Let's get started on this first question. A 480 50 Hz delta connection synchronous generator has the open circuit characteristics shown below. So this generator has a reactance. So if you look at the equivalent circuit, single phase equivalent, then the reactance is 0.1. And the little resistor here is 0.015. Okay, and we have a high voltage here because the voltage flow to the other side, okay, to the terminal, because this is generator. And at the full load, the machine supply this amount of current at this power factor, and under full load condition, and there are some losses. Okay, and let's look at the first one. So how much field current must be supplied to the generator to make the terminal voltage 480 at no load. So if this one is 480 at no load, the current is zero because there's no load. So there's no voltage drop. So we can see that this one is also 480. And for 480, in order to generate this amount of internal voltage, and then we need a excitation current, okay, and the current have this relationship. So we just draw this one and read from the table. It's 4 point something. Okay, I think the answer choose 4.5, so something around that. Okay, that's the first question ticked. The second question, all right, so if the generator is now connected with this load, is a full load, okay, and how much field current will be required to keep the terminal voltage at 480? Okay, we still want a 480 at the terminal. At this time, a very heavy current being drawn from the load, so there will be voltage losses. Okay, so we need to calculate this voltage drops across those impedance. Then we know the internal voltage needed, and then we're going to read the table again. I'm expecting much higher current needed to generate a higher voltage. All right, let's do that. So there's a bit trick here. So the generator is connected in, it's not like that, it's the delta connection. Okay, the generator is connected in a delta connection, something like that. Okay, sorry about the drawing. Okay, they are connected. So there is one line, there's one line, there's another line. Okay, and the terminal voltage here is a 480. We can set this as a reference to give a 0 degree. Okay, now we want to know, okay, let me change the color. I want to know how much the current flow here, because that is the equivalent current here, IA, right? We want to know how much IA. But what we've been given is 120 is talking about here. So that's this, 1200 amp is talking about this. This is the line current. And if you remember, the line current, so IAA, that's the line current. Okay, for delta connection, that's from the second year circuit theory. That's the line current, and that's the phase current. Okay, so the phase current is smaller than line current. Then we can figure out here that the IA, the phase current, absolute value is 120. Is 1200 divided by root 3. Okay, and that equals to 692.8 amp. So next is, what is the angle of this current? Okay, another information we've been given is the power factor. Okay, power factor is cosine theta is 0.8 lagging. Okay, and this information given is, but you have to pay attention here. This power factor is talking about phase voltage versus phase current. Okay, is not the power factor at the terminal, because the terminal is related to the line voltage and the line current. We're not talking about that. We're talking about the phase voltage. In this case, phase voltage and line voltage are the same, but it's versus the phase current as well. Okay, the phase current here is the IA. All right, so we know the phase voltage is 0 degree. 580 volts, 0 degree, and the arc cosine 0.8 gives us some angle 36.87 because of lagging. So this current IA equals to that magnitude and negative 36.87 degree. Okay, so we got this IA now. Then we can calculate this voltage here. So you can see that EA going to equals to the terminal voltage VT plus a impedance RA plus JXS IA. Okay, if you plug in number, that's 480, 0 degree, plus a number here, 0.015 plus J, 0.1, multiply with this number, this vector, or phasor, okay? And then probably use your calculator to do that. Then you will find EA equals to 532 with a 5.3 angle volt. Okay, so we need a 532 volts. Then we need raise this again to find the IF, the field current needed is 5.7, something around that, by rate from the graph. Okay. All right, so next part, how much power is generated? Is the generator now supplying? How much is supplying? We have this amount of voltage go there, right? So the third one is P out. This is output power, gonna equals to the voltage here multiply the current here, right? So this voltage cross the generator, and the current flows outside from this generator. So we need to use this phase current instead of this line to line current. Okay, line current. So we need to have 3 phase, and each phase is the phase voltage multiply with so we just calculate the apparent power here. It's 1200 divided by root 3. Okay, that's the phase current, this IA we just did, and multiply with a cosine theta, which is 0.8. Okay, that's 0.8, and then if we do that, we got the answer. Okay, and you can read from the answer booklet. And the next one is how much power is supplied to the generator by the prime mover. Okay, So now we need to bring up this one. Okay. All right, it's becoming good. All right, so the next part is we talked about, so everything is from prime mover. Okay, everything's come from the prime mover. All right, so section 3, we got to say 798 kilowatt, and that is actually the final output. I bring out this flow chart. So that's the final output power to the load, and during that we do not have this one. So if you look at here, then we have the friction losses 40, and this one is 30, and then we know that Pn equals to 798 plus a 40 plus a 30, and also add a and we have this I square R losses. So we already have this IA number, so square R losses, and we just add everything together. And got this 889.6 kilowatt. Okay. All right, so that's number 4, I believe. And number 5, what is the machine overall efficiency? Okay, so the efficiency is output divided by the input. Okay, so number 5, we got the efficiency is output divided by input. Okay, input is a larger amount of power. Next, if the generator load were suddenly disconnected from the line, what would happen to its terminal voltage? Okay, for the terminal voltage, if suddenly it lost the load, your excitation current doesn't change, right? You still have that excitation current, so your internal voltage EA is 532, okay? And at that moment, you have a 532 volts internal voltage, and suddenly there's no voltage losses because there's no current IA equal to 0, then your output voltage will be 532 volts, okay? Your internal voltage will be passed to the terminal. And the last one, suppose that the generator is connected to a load drawing this amount of power, but this time is a leading. So how much field current would be required? Okay. So for this time, I make copy from here. This is still making sense. Okay. So this equation is still making sense. Copy paste for number 7. Okay. So for number 7, the internal voltage EA is still equals to this one time, but this time the angle changes. Okay, instead of a lagging, we got a leading voltage. Let me change the color to highlight the difference here. Okay, so this becomes a positive angle. All right, if you do the calculation here, then you will find that's number 7. You got that 451 volts and 7.1 degree. So 451, then you're going to have a smaller current required. 451. Rate from the table again, you got that excitation current needed. All right, so that's for the first question.